Super-Kamiokande is a neutrino observatory located under Mount Ikeno near the city of Hida, Gifu Prefecture, Japan. The observatory was designed to search for proton decay, study solar and atmospheric neutrinos, and keep watch for supernovae in the Milky Way Galaxy. Description: the Super-K is located 1,000 meters underground in the Mizumi mine in Hida's Kamioka area. It consists of a cylindrical stainless steel tank that is 41.4 meters tall and 39.3 meters in diameter, holding 50,000 tons of ultra-pure water. The tank volume is divided by a stainless steel superstructure into an inner detector region that is 33.8 meters in diameter and 36.2 meters in height, an outer detector which consists of the remaining tank volume. Mounted on the superstructure are 11,146 photomultiplier tubes 50 centimeters in diameter that face the ID and 1,885 20 centimeters PMTs that face the OD. There is a Tyvek and black sheet barrier attached to the superstructure that optically separates the ID and OD. A neutrino interaction with the electrons or nuclei of water can produce a charged particle that moves faster than the speed of light in water. This creates a cone of light known as Cherenkov radiation, which is the optical equivalent to a sonic boom. The Cherenkov light is projected as a ring on the wall of the detector and recorded by the PMTs. Using the timing and charge information recorded by each PMT, the interaction vertex, ring direction and flavor of the incoming neutrino is determined. From the sharpness of the edge of the ring, the type of particle can be inferred. The multiple scattering of electrons is large, so electromagnetic showers produce fuzzy rings. Highly relativistic muons, in contrast, travel almost straight through the detector and produce rings with sharp edges. Detector: the Super-Kamiokande is a Cherenkov detector used to study neutrinos from different sources including the Sun, supernovae, the atmosphere, and accelerators for proton decay. The experiment began in April 1996 and was shut down for maintenance in July 2001, a period known as SKI. Since an accident occurred during maintenance, the experiment resumed in October 2002 with only half of its original number of IDPMTs. In order to prevent further accidents, all of the IDPMTs were covered by fiber-reinforced plastic with acrylic front windows. This phase from October 2002 to another closure for an entire reconstruction in October 2005 is called SK2. In July 2006, the experiment resumed with the full number of PMTs and stopped in September 2008 for electronics upgrades. This period was known as SK3II. The period after 2008 is known as SKIV. The phases and their main characteristics are summarized in Table 1. SKIV upgrade: in the previous phases, the IDPMTs process signals by custom electronics modules called analog timing modules. Charge to analog converters and time to analog converters are contained in these modules that had dynamic range from 0 to 450 picocoulomb with 0.2 picocoulombs resolution for charge and from -300 to 1000 nanoseconds with 0.4 nanoseconds resolution for time. There were two pairs of QAC TAC for each PMT input signal. This prevented dead time and allowed the readout of multiple sequential hits that may arise, e.g., from electrons that are decay products of stopping muons. The SK system was upgraded in September 2008 in order to maintain the stability in the next decade and improve the throughput of the data acquisition systems. QTC-based electronics with Ethernet. The QBE provides high-speed signal processing by combining pipelined components. These components are a newly developed custom charge-to-time converter in the form of an application-specific integrated circuit, a multi-hit time-to-digital converter, and field-programmable gate array. Each QTC input has 3 gain ranges: small, medium, and large. The resolutions for each are shown in table. For each range, analog to digital conversion is conducted separately, but the only range used is that with the highest resolution that is not being saturated. The overall charge dynamic range of the QTC is 0.2–2500 picocoulombs, 5 times larger than the old. The charge and timing resolution of the QBEE at the single photoelectron level is 0.1 photoelectrons and 0.3 nanoseconds respectively. Both are better than the intrinsic resolution of the 20 PMTs used in SK. The QBEE achieves good charge linearity over a wide dynamic range. The integrated charge linearity of the electronics is better than 1%. The thresholds of the discriminators in the QTC are set to -0.69 mV. This threshold was chosen to replicate the behavior of the detector during its previous ATM-based phases. Water tank. The outer shell of the water tank is a cylindrical stainless steel tank with 39 meters in diameter and 42 meters in height. The tank is self-supporting, with concrete backfilled against the rough-hewn stone walls to counteract water pressure when the tank is filled. The capacity of the tank exceeds 50 kt of water. PMTs and associate structure. The basic unit for the ID PMTs is a supermodule, a frame which supports a 3x4 array of PMTs. Supermodule frames are 2.1 meters in height, 2.8 meters in width and 0.55 meters in thickness. These frames are connected to each other in both the vertical and horizontal directions. Then the whole support structure is connected to the bottom of the tank and to the top structure. In addition to serving as rigid structural elements, supermodules simplified the initial assembly of the ID. Each supermodule was assembled on the tank floor and then hoisted into its final position. Thus the ID is in effect tiled with supermodules. During installation, ID PMTs were pre-assembled in units of 3 for easy installation. Each supermodule has 2 OD PMTs attached on its backside. The support structure for the bottom PMTs is attached to the bottom of the stainless steel tank by one vertical beam per supermodule frame. The support structure for the top of the tank is also used as the support structure for the top PMTs. Cables from each group of 3 PMTs are bundled together. All cables run up the outer surface of the PMT support structure, i.e., on the OD PMT plane, pass through cable ports at the top of the tank, and are then routed into the electronics huts. The thickness of the OD varies slightly, but is on average about 2.6 meters on top and bottom, and 2.7 meters on the barrel wall, giving the OD a total mass of 18 kt. OD PMTs were distributed with 302 on the top layer, 308 on the bottom, and 1275 on the barrel wall, to protect against low-energy background from radon decay products in the air. The roof of the cavity and the access tunnels were sealed with a coating called MineGuard registered sign produced by Euralone in Canada. MineGuard registered sign is a spray-applied polyurethane membrane developed for use as a rock support system and radon gas barrier in the mining industry. The average geomagnetic field is about 450 mg and is inclined by about 45 degrees with respect to the horizon at the detector site. This presents a problem for the large and very sensitive PMTs which prefer a much lower ambient field. The strength and uniform direction of the geomagnetic field could systematically bias photoelectron trajectories and timing in the PMTs. To counteract this, 26 sets of horizontal and vertical Helmholtz coils are arranged around the inner surfaces of the tank. With these in operation, the average field in the detector is reduced to about 50 mg. The magnetic field at various PMT locations were measured before the tank was filled with water. A standard fiducial volume of approximately 22.5 ktons is defined as the region inside a surface drawn 2.00 meters from the ID wall to minimize the anomalous response caused by natural radioactivity in the surrounding rock. Monitoring system. Online monitoring system. An online monitor computer located in the control room reads data from the DAQ host computer via an FDDI link. It provides shift operators with a flexible tool for selecting event display features, makes online and recent history histograms to monitor detector performance, and performs a variety of additional tasks needed to efficiently monitor status and diagnose detector and DAQ problems. Events in the data stream can be skimmed off, and elementary analysis tools can be applied to check data quality during calibrations or after changes in hardware or online software. Real-time supernova monitor to detect and identify such bursts as efficiently and promptly as possible. Super-Kamiokande is equipped with an online supernova monitor system. About 10,000 total events are expected in Super-Kamiokande for a supernova explosion at the center of our galaxy. Super-Kamiokande can measure a burst with no dead time, up to 30,000 events within the first second of a burst. Theoretical calculations of supernova explosions suggest that neutrinos are emitted over a total time scale of tens of seconds, with about a half of them emitted during the first 1 or 2 seconds. The Super-K will search for event clusters in specified time windows of 0.5, 2 and 10s. Data are transmitted to real-time SN watch analysis process every 2 min. Analysis is completed typically in 1 min. When supernova event candidates are found, is calculated if the event multiplicity is larger than 16, where mean is defined as the average spatial distance between events, i.e., neutrinos from supernovae interact with free protons, producing positrons which are distributed so uniformly in the detector that for SN events should be significantly larger than for ordinary spatial clusters of events. In the Super-Kamiokande detector, mean for uniformly distributed Monte Carlo events shows that no tail exists below 1000 centimeters. For the alarm class of burst, the events are required to have 900 cm for 25, 40 or 750 cm for greater than 40. These thresholds were determined by extrapolation from SN19878 data. The system will run special processes to check for spallation muons when burst candidates meeting alarm criteria, and make a primarily decision for further process. If the burst candidate passes these checks, the data will be reanalyzed using an offline process and a final decision will be made within a few hours. During the Super-Kamiokande running, this never occurred. One of the important capabilities for Super-Kamiokande is to reconstruct the direction to supernova by neutrino electron scattering. A total of 100 to 150 events are expected in case of a supernova at the center of our galaxy. The direction to supernova can be measured with angular resolution, where n is the number of events produced by the new E scattering. The angular resolution, therefore, can be as good as delta theta 3 degrees for a supernova at the center of our galaxy. In this case, not only time profile and the energy spectrum of a neutrino burst, but also the information on direction of supernova can be provided. Slow control monitor and offline process monitor. There is a process called the slow control monitor as part of the online monitoring system. Watches the status of the HV systems, the temperatures of electronics crates and the status of the compensating coils used to cancel the geomagnetic field. When any deviation from norms is detected, it will alert physicists are prompt to investigate, take appropriate action, or notify experts. To monitor and control the offline processes that analyze and transfer data, a set of software was sophisticatedly developed. This monitor allows non-expert shift physicists to identify and repair common problems to minimize downtime, and the software package was a significant contribution to the smooth operation of the experiment and its overall high lifetime efficiency for data-taking research. Solar neutrino, also see neutrino oscillation. The energy of CERN comes from the nuclear fusion in its core, where a helium atom and an electron neutrino are generated by 4 protons. These neutrinos emitted from this reaction are called solar neutrinos. Photons, created by the nuclear fusion in the center of the Sun, take millions of years to reach the surface. On the other hand, solar neutrinos arrive at the Earth in 8 minutes due to their lack of interactions with matter. Hence, solar neutrinos make it possible for us to observe the inner Sun in real time. That takes millions of years for visible light. In 1999, the Super-Kamiokande detected strong evidence of neutrino oscillation that successfully explained the solar neutrino problem. The Sun and about 80% of the visible stars produce their energy by the conversion of hydrogen to helium via. Consequently, stars are a source of neutrinos, including our Sun. These neutrinos primarily come through the pp chain in lower masses, and for cooler stars, primarily through CNO chains of heavier masses. In the early 1990s, particularly with the uncertainties that accompanied the initial results from Kamioka 2 and the Ga experiments, no individual experiment required a non-astrophysical solution of the solar neutrino problem. But in aggregate, the Kamioka 2 and Ga experiments indicated a pattern of neutrino fluxes that was not compatible with any adjustment of the SSM. This in turn helped motivate a new generation of spectacularly capable active detectors. These experiments are Super-Kamiokande, the Sudbury Neutrino Observatory, and Ikeno. Super-Kamiokande was able to detect elastic scattering events which, due to the charged current contribution to scattering, has a relative sensitivity to S and heavy flavor neutrinos of 7:1. Since the direction of the recoil electron is constrained to be very forward, the direction of the neutrinos are kept in the direction of recoil electrons. Here is provided whereas the angle between the direction of recoil electrons and the Sun's position. This shows that the solar neutrino flux can be calculated to be, comparing to the SSM, the ratio is. The result clearly indicates the deficit of solar neutrinos. Atmospheric neutrinos are secondary cosmic rays produced by the decay of particles resulting from interactions of primary cosmic rays with Earth atmosphere. We classified the observed atmospheric neutrino data into 4 types. Fully contained events have all the tracks in the inner detector, while partially contained events have escaping tracks from the inner detector. Upward through-going muons are produced in the rock beneath the detector and go through the inner detector. Upward stopping muons are also produced in the rock beneath the detector but stop in the inner detector. The observed number of neutrinos is predicted uniformly regardless the zenith angle. However, Super-Kamiokande found that the number of upward-going muon neutrinos is half of the number of downward-going muon neutrinos in 1998. This can be explained that neutrinos changes or oscillated into some other neutrinos that are not detected. This is called neutrino oscillation, and this discovery indicates the finite mass of neutrinos and suggests to extend the Standard Model. Neutrinos oscillate in 3 flavors and all neutrinos have their rest mass. Later analysis in 2004 suggested a sinusoidal dependence of the event rate as a function of length, energy, which confirmed the neutrino oscillations. K2K experiment. The K2K experiment was a neutrino experiment from June 1999 to November 2004. This experiment was designed to verify oscillations observed by Super-Kamiokande through muon neutrinos. It gives first positive measurement of neutrino oscillations in conditions that both source and detector are under control. The Super-Kamiokande detector plays an important role in the experiment as the FAR detector. Later experiment T2K experiment continued as the second-generation follow-up to the K2K experiment. T2K experiment T2K experiment is a neutrino experiment collaborated by several countries including Japan, United States and others. The goal of T2K is to gain deeper understanding of parameters of neutrino oscillation. T2K has made a search for oscillations from muon neutrinos to electron neutrinos, and announced the first experimental indications for them in June 2011. The Super-Kamiokande detector plays as the FAR detector. The Super-K detector will record the CERN radiation of muons and electrons created by interactions between high-energy neutrinos and water. Proton decay. Proton is assumed to be absolutely stable in Standard Model. However, the grand unified theories predict that can decay into lighter energetic charged particles such as electrons, muons, pions or others which can be observed. Kamiokande helps to rule out some of the theories. Super-Kamiokande is currently the largest detector for observation of proton decay.